And a question about some of the other graph algorithms that we have. Flow here is a very common and very understandable idea. The idea being, if we were to model in our data some capacity for these edges, can we figure out where something might be blocked up? So let's take a look. Here, let us model a very simple graph with 4 nodes. And we'll put a capacity measurement on every single node here. If I show this, you'll see these are my 4 nodes, and this is the capacity. And I have a planar representation here. If I move off to the side, you can see there's node B here. And you can see from A to D, I basically have 2 paths, 1 through C and 1 through B. And I have the capacity notated here. And so you might say, what is the maximum throughput that we might be able to get through this graph? What does this graph really mean? Well, if this is an actual flow problem, like for example, I have 2 internet connections, and the 2 internet connections might have to go through a particular hop or a particular router, and might be able to measure the speed along each one of the edges here. What's the maximum that I can upload to Dropbox at any one point in time? It might also be the case that this represents some sort of workflow. Maybe these are entities, maybe these are people, and these are the number of requests or number of tasks or number of jobs that they can do in a unit of time, but there might be an approval process in the middle, and that approval process might create a bottleneck. Min and max flow is often about figuring out what your maximum throughput is and then identifying where the bottlenecks are. And you can see, even beyond the purely mathematical examples, this has direct applicability even to very standard business problems. Well, in NetworkX, it is very easy for us to ask graphs like this what their maximum flow is. In fact, we can just ask, give me the maximum flow. And in fact, here, let me ask this graph what its maximum flow is. I can say, give me the maximum flow from G, or on G, from A to D, and it'll tell me exactly how it wants me to construct that flow. And let's get from NetworkX algorithms. Here we go. And when I do that, you'll see it gives me 2 pieces of information. The first piece of information is the maximum flow. You can see here it's a maximum flow of 2, and it gives me a brand new modeling of this graph that tells me what the graph would look like under the maximum flow. And so if I take this data, I can even model what percentage of my throughput is being used. And so I might have to code this here. I can say, well, what I'm going to do is I'm going to get the max flow graph. So this is my max flow graph. And instead of modeling this with the edge data, I can model this with what the max flow graph actually has for that edge data for each one of these nodes. So here we go. And this should give me the ability to, and that's good there. And then what I should be able to see is, where do I have bottlenecks? And let's actually present this as a percentage, just so we can see exactly where bottlenecks may appear in our graph. So here we go. And so you can see, and let's do this, 0.0f. And so you can, oops, and let's go there. And so you can see the problem is really this node here. We only have 10% throughput on this. We have such high capacity, and we're basically using this capacity. We only have 10 throughput. This has been over allocated. This process is either too efficient or needs to be upgraded in order to give me the best chance of improving this flow. That's where max flow shows up, as well as the next thing we're going to talk about, which is minimum cut. It's often about trying to identify from some process where can I strategically add more resources to improve this process, because clearly if I add more resources to this edge, it will not make a difference. It will not improve my overall throughput. It's this edge here and this edge here that are blocking everything. Minimum cut is another mechanism by which we might partition our data. Minimum cut's the idea that given a particular graph, where can I cut this graph in order to separate all the nodes into 2 separate nodes? This requires that this graph be cuttable, bipartite, and the goal here would be, how do I construct those 2 parts such that the edges that are crossed in that cut are the minimum possible edges? For those of you who are interested in machine learning, you may have seen minimum cut before. It comes up in some machine learning tasks, image recognition tasks. It comes up in things like trying to remove things from images programmatically. You construct a graph where the nodes represent the portions of that graph and the edges represent some information about the locality or the connectivity or the color differences or whatnot. And then you can figure out how to partition things, how to cut things out by minimizing over this quantity. But again, NetworkX makes our life very easy. It gives us the ability to ask for what is the minimum cut, what's the flow of that cut. So it's going to cut across these two edges here and here. And what are the sets that it produces? And you can see that I can even graph it, and you can see it cut that graph into two parts on the two edges that are of side one. And so you can see it's trying to partition this graph into two groups with some minimization factor based on the edge data. We can think a lot of these algorithms really do come down to things like partitioning the data set or finding ways to group nodes together. There is another thing that you may discover comes up when you talk about all of these, the idea of the click. If we happen to have a graph and we want to find what the maximally interconnected subgraphs are, for example, we have some connectivity of who's friends with whom. What are the closed groups where everybody is friends with everybody else in that group? That's what a click is in common parlance, and that's what a click is in the language of graphs. Here, we have a bunch of edges, and I've removed two edges from the full connectivity example, and I can ask NetworkX, give me all the possible clicks. Give me all the possible ways that I could group nodes together so that every node is connected to every other node. And I get some trivial answers, like every node all by itself. And I get some interesting answers here. These are the dual partnerships where this is symmetric. And I get some very interesting answers here where I can see that BAC forms one click and BCD forms another click. I can even ask to find the maximal size clicks, and you can see here, these are the maximal size clicks. And so if my network represented an actual human network, and I wanted to find what are the groupings of friends, maybe that gives me some information about who I want to target for an advertising campaign, it segments this graph into these perspectives. Well, maximum clicks is exactly the way I want to do this. And we'll see that if I look at this graph, it might be hard for me to visualize it, but you can see D, E, and F, they're all connected to everything else. C, E, and D are connected to everything else. A, C, and B, that's another click. And if I want to find a click which maximizes the size of all the clicks, partitioning these, well, that's exactly what that is. All of these algorithms really show you that what you can do with these graphs is construct them, figure out how to model the aspects of the problem that you want to solve in the form of these nodes and these edges. These nodes don't have to really be homogeneous entities. Sometimes they can be people and the jobs they match to, and then apply right out of the box these NetworkX algorithms, which will solve these problems for you. Whether or not you want to do this for actual problems that you might encounter in machine learning, clustering algorithms, or some sort of image segmentation, well, you probably want to use the underlying algorithms, but you probably don't want to use NetworkX. In these examples, we can see we have fairly small graphs, and the algorithms completed very effectively, and the results we can actually do something with.